This next section talks about buffers. And a buffer is a solution containing appreciable amounts of both a weak acid and its conjugate base, or a weak base and its conjugate acid. Remember that conjugate base is going to be a salt of that particular acid, or the conjugate acid is going to be a salt of that particular base. The buffer solutions resist changes in pH upon additions of a small amount of strong acid or base. The examples that we're going to be including here are essentially those involving the acetate ion. So it's going to be acetic acid and sodium acetate. One that you commonly encounter in the hospital situation is the bicarbonate ion in the blood solution. This photograph illustrates the benefits of what it can be for a buffering solution. So here you've got on the left-hand side unbuffered and buffered solutions at the same pH of 8, and they're basic as shown by the color, yellow color of the indicator methyl orange. On the right-hand side, to each of those solutions has been added 1 milliliter of a 0.1 molar hydrochloric acid solution. And you can see that there's virtually no change at all in the color of the buffered solution, but there's a dramatic change in the color of the unbuffered solution. So what we'll do is consider a buffer, HA, which for our case will be acetic acid, and then on the other side will be the acetate ion. Buffers are good at getting rid of strong acids and strong bases, or minimizing essentially the effect. So any added hydroxide ion or hydronium ion is consumed and therefore does not directly affect the pH. Any added hydroxide ion is converted to the weak base, as shown by that first equation, and any added hydronium ion is converted to the weak acid. Therefore, the buffers can be used to maintain nearly constant pH. And so let's continue on to this slide right here. You can see where we're starting off in the middle here. You've got a buffered solution equimolar in both the acid, acetic acid, and the acetate base. If you, to that buffered solution, if you were to add a hydronium ion, in other words a strong acid, you can see that the concentration increases of the acetic acid and there's a decrease proportionally of the acetate ion. So the hydronium ion added shifts the position to the left, but it's a modified amount. Likewise, if you were to add a hydroxide ion to that, you can see that there's a downward shift in the acetic acid, but an increase in the acetate ion. So there's an example on page 797, example 14.2. And what that does is they work through that. They're calculating out the pH of the acetate buffer. And of using the information that they provide to you, you can determine that the concentration of the hydronium ion is 1.8 times 10 to the minus fifth for a pH value of 4.74. What they've done is they've then said, okay, the next part B of that is they add 1 milliliter of a 0.1 molar sodium hydroxide solution is added to there. Now, in your book it says you're adding a strong acid, but that's absolutely not the case. Sodium hydroxide is a strong base. That's just a typo. And that's going to neutralize a portion of the acetic acid. And if you go through the whole calculation there, you'll see that the pH changes from a pH of that's 4.74 to a pH of 4.75. So it's only a 0.01 change. As a comparison, what they did is they said, okay, what happens if you did this to an unbuffered solution? If you had something that starts at 4.74 and was not buffered, and you added that same 1 milliliter of that 0.01 molar sodium hydroxide, And you'll see in that case, going through the calculations, the pH changes to 10.99, a dramatic shift in the pH. So the buffer capacity is the amount of strong acid or base that can be added to a given volume of a buffered solution before the pH changes significantly. All buffers have a limited capacity of how much hydronium ion or hydroxide they can soak up. Eventually, all of the acid reacts upon the addition of the hydroxide ion, or all of the acetate ion reacts with the added hydronium ion. So the buffer capacity depends upon the number of moles of the weak acid and its conjugate base that are present in the mixture. The more moles of buffer components leads to a higher buffering capacity. Once the buffer components near depletion, you'll see a dramatic increase in the pH. And you can determine the pH of a buffer solution by doing the calculation as shown in using the same type of formula, doing this type of Henderson-Hasselbalch equation. This is what is used to calculate the pH of a buffer. The pH equals the pKa plus the log of the acetate ion in this particular case divided by that of the acetic acid concentration. And if you have two different buffered solutions, a 1.1 molar in each of those or a 0.1 molar, and you can compare the differences. What's going to happen is you're going to get a change in pH, and it depends upon, in this particular case, the number of milliliters of 0.1 molar sodium hydroxide that is added. So initially you've got 100 milliliters of a buffered solution. And you can see that you're able to add, and there's only a slight increase in that pH, all the way until you get to 80-90%, and then once it hits the about 95%, it starts shooting up pretty dramatically. Now, the next part has to do with acid-base titrations. And this is a key thing that if we were doing a lab, we'd be doing, I've got something in mind. We'll probably work on something along these lines. But remember, you can analyze an acid by reacting with a known concentration of the other. You can have a strong acid, strong base type of titration, or you can have a weak acid, strong base type of titration. Now, the equivalence point means that the amount of titrant added, how much you've added through your burette there, is equal to the amount of analyte present in the solution down below. If it's a strong acid and strong base, usually it's the equivalence point is about pH 7. So let's first talk about the strong acid, strong base titration. The initial pH is very low since you've got a strong acid, and it's going to be a very gradual rise in pH as a base is added. So for this hydrochloric acid sodium hydroxide titration, where you're adding sodium hydroxide to the hydrochloric acid, you eventually get the water plus the sodium chloride salt. So eventually, as you go through that, you are going to get to a pH until it swamps out, and then eventually you'll just be adding material where the base cannot be neutralized to form the salt. The midpoint of the vertical part of the curve is the equivalence point. pH is the equivalence point of 7. Excess sodium hydroxide controls the pH after that equivalence. So if in a weak acid strong base titration, instead, for example, in this case, we have the acetic acid plus sodium hydroxide forming the sodium acetate and water. Many features of the titration curve are similar, but the titration curve is a bit more complex. It's going to start off slow and not as low as a strong acid titration. A strong acid titration is going to start off down around pH of 1, whereas we know that the sodium acid, acetic acid one is going to start off closer to 4.74. And there's a gradual rise in pH as the base is added. Eventually, the pH rises very rapidly, and the midpoint of the curve is the equivalence point. Here, it's going to be at 8.72. Beyond that, the sodium hydroxide controls the equivalence point. And this shows exactly those two titrations. You're starting off at a pH of 1 for the hydrochloric acid, and you're adding it. Very, very little change there. It starts changing dramatically when you get up towards the 25. And then a single drop here is critical when you're doing these titrations. Whereas when you are doing it with the titration of a weak acid, you can see it starts off at a much higher level. We must have a little different concentration here, yes, than we had at the other one, because this starts off at a 3. And then it goes up, and you can see that at the equivalence point is an 8.72 in this particular example. So 1 or 2 drops of indicator are usually added to the sample being titrated. The acid-base indicator is useful in determining the equivalence point in the titration. The pH at which the indicator color changes is called the endpoint. And you want to choose an indicator that is an endpoint that coincides as close as possible to that equivalence point. Indicators are usually weak acids. Weak acid is a different color than its conjugate base. And this chart right here shows the range of colors that are possible for several of these different acid-base indicators. Likewise, you can have this right here showing 3 different types of ones, where how methyl orange would change. It would change way down there once you got up to a 3.5, whereas the litmus pH range changes at pH of 7, and the phenolphthalein changes at about a pH of about 8.8. You need to have an indicator that will give you exactly what you need there. And that's the end of that chapter.